The buffer ring allocation strategy defines a fixed-size circular queue for managing memory buffers in sequential write patterns. The implementation maintains a contiguous memory region divided into equally sized slots. Each slot holds a single data unit. The ring cursor advances monotonically, wrapping at the boundary to the beginning. Allocation occurs at the head position. Consumption occurs at the tail. The distance between head and tail defines occupancy. Initialization allocates the ring buffer through contiguous heap allocation. The size parameter specifies the total number of slots. Memory is 0 during allocation. The head and tail cursors begin at index 0. The slot size must be a power of 2 to enable efficient modulo operations using bitwise and slot indices are tracked as unsigned 32-bit integers. Wraparound occurs implicitly when indices exceed the maximum representable value. The write operation acquires the current head position and advances it by 1. The slot at the head position is populated with data. No bounds checking occurs during write. If the head catches the tail, the oldest data is silently overwritten. The writer must coordinate with the reader to avoid this condition. Write operations are non-blocking and require no locking in single producer configurations. The read operation fetches the current tail position and examines the slot. If tail equals head, no data is available. The reader advances tail by 1 after consuming data. Read operations do not block. If tail reaches head, subsequent reads return empty state. Multiple readers must each maintain separate tail cursors. Shared tail cursors require synchronization primitives. Occupancy is calculated as the difference between head and tail cursors, modulo the ring size. This value represents the number of unread slots. Occupancy updates are eventual and may lag behind actual state if readers and writers operate concurrently. Empty state occurs when occupancy equals 0. Full state occurs when occupancy equals ring size -1. Full state prevents further writes without overwriting. Wraparound behavior uses modular arithmetic on cursor indices. The actual index into the allocation is computed as cursor and size -1. This bitwise operation replaces division and modulo, reducing latency. Wraparound is transparent to the caller. Cursors may exceed the nominal ring size indefinitely. The ring operation maintains the same slot access pattern. Multi-producer scenarios require atomic operations on the head cursor. A compare and swap primitive advances head only if no other producer has modified it. Failed attempts must retry. Producers may spin or back off before retrying. The atomic operation maintains ordering guarantees across processors. Memory barriers are inserted implicitly by the atomic operation. Multi-consumer scenarios require atomic operations on the tail cursor. The same compare and swap pattern applies. Consumers coordinate slot ownership through atomic tail advancement. Failed consumers retry their operation. The atomic operation enforces that each slot is consumed exactly once. No duplicate or lost reads occur under correct synchronization. Burst capacity defines the maximum allowable occupancy for sustained throughput. Bursts exceeding this threshold trigger backpressure signaling. Writers may block or drop data depending on policy. Burst capacity is typically ring size divided by 4. This threshold provides buffer for latency spikes. Exceeding burst capacity indicates a consumer stall. The reset operation reinitializes both cursors to 0, discarding all buffered data. The memory is not reallocated. Slots retain their previous contents but are no longer logically valid. Reset requires coordination with both producers and consumers. All in-flight operations must complete before reset is safe. Reset is typically invoked during error recovery. Slot data layout is application defined. Each slot may contain a struct, scalar value, or variable length header with pointer. The slot size parameter enforces uniform allocation. Variable length data requires an out-of-band memory pool. Slot size must be fixed at compile time or configuration time. Slot alignment matches natural boundaries for the contained type. Memory locality is optimized by the contiguous allocation strategy. All slots reside in a single cache line during sequential access. Producer and consumer cursors may occupy separate cache lines to avoid false sharing. The ring structure provides predictable prefetching behavior for hardware cache controllers. Temporal locality is maximized when occupancy is high. The monitoring interface exposes occupancy, peak occupancy, and overwrite count metrics. Occupancy is sampled at fixed intervals. Peak occupancy records the maximum occupancy since last reset. Overwrite count increments when write catches tail. These metrics inform tuning decisions. Metrics are non-blocking reads from cursor positions. Deallocation releases the contiguous memory region through heap-free operations. Deallocation must occur after all readers and writers have exited. In-flight operations may corrupt state if deallocation is premature. A reference counter may track active accessors. Once counter reaches 0, deallocation is safe. Memory is returned to the allocator. Size selection depends on expected latency, throughput, and buffering depth. Small rings minimize latency but risk overwrite. Large rings reduce overwrite risk but consume memory. Typical sizes range from 256 to 65,536 slots. Size must be a power of 2. Undersizing causes frequent overwrites. Oversizing wastes memory with negligible latency gain. Error conditions include overwrite detection, allocation failure, and synchronization timeout. Overwrite is detected by comparing head and tail. Allocation failure returns null or exception state. Synchronization timeout occurs if atomic operations fail repeatedly. Degraded modes may drop data or reduce throughput. Recovery requires investigation of root causes and system reconfiguration.